Shall we start?
Yeah, I'm starting.
Okay, we will just introduce you and then you can go on.
Okay.
Okay, good morning, everyone. Welcome to the fourth day of the online limit camp. Today we have with us Debatra. He just completed his B.Math from ISI Bangalore and he'll be speaking about the probabilistic landscapes and additive combinatorics. Over to you, Debatra.
Thank you. So today I'm going to give a talk on, as the title suggests, probabilistic landscape of additive combinatorics. Or in this talk, I'm going to discuss about how probability theory, or in particular, probabilistic methods, are used to study the subject additive combinatorics. I assume many of you know a thing or two about this subject, or those who are new to this topic. This is a modern branch in mathematics where we study about the combinatorial structure of a set, or in particular, combinatorial structures of additive sets. Now, additive sets are nothing but subsets of additive abelian group. So I think you all know about abelian group. Subset of any additive abelian group, such as set of real numbers under addition. Subset of any such additive abelian groups are called additive sets. So in additive combinatorics, we generally talk about these kind of additive sets and their combinatorial structure, like their cardinality, their energy, and uh, so on. And this subject is itself useful in various other mathematical branches, such as number theory, mainly in number theory, but also in graph theory, and also in data science and cryptography and all. So this is a rich branch in mathematics, and currently even Terence Tao is working on this subject as well. So the probabilistic methods in combinatorics, this particular topic is first pioneered by Paul Ardosh. And in today's talk, I'm just going to give some proofs of some Ardosh's theorem, and we are going to discuss how we can apply probabilistic techniques to derive some beautiful results in this subject. So in the first slide, I have written the what is additive combinatorics and its significance. And as you can see that I have written here that we work inside abelian groups, as I have just told you, and it seeks to understand how sets behave under operations such as addition and what this reveals about their internal structure. So there are many properties. Suppose you take any additive set A, then how many non-trivial quadruples are there in the set A such that they satisfy the relation A plus B equal to C plus D? This kind of things, this number is called energy of the set A. What this energy of the set actually reveals about the set? If this energy is high, then how the set will react? If this energy is low, then how the set will react? These kind of things we are going to discuss in today's topic. And here I've written some examples of some highly structured sets, such as AP subgroups. If you take any additive abelian group and take any subgroup of it, those sets are highly structured. You can say so many things about those sets. But if you take some random set, suppose take the group R, or set of all real numbers, and take the subset, the set of all primes inside of it, then definitely uh, can't say much things about these kind of sets. Then in order to study these random sets, we need probability. And this highly structured set can display constant growth under addition, where once again this random or pseudo random set don't. Now, why the subject is important? Once again, it is highly influential in the field like number theory, harmonic analysis, theoretical computer science, graph theory, and all of this stuff. Now, this is a basic introduction of this subject. Now, we are going to go into the main talk. So, first, proving the important results using probabilistic techniques, we first need to know about some definitions. Okay. So, it is the aim of the talk. So here are some basic definitions. An additive group is nothing but an abelian group under the operation addition. It is called additive abelian group. And any subset of that additive abelian group, not necessarily subgroup, is called additive set. So for example, take a set of all real numbers and take any arithmetic progression inside of this, or as I've told you, set of all primes or anything. Doesn't need to be subgroup. So these sets are called additive sets. Under the definition of additive set, we can define some other notations, such as subset. So take any two additive set A and B. The subset is defined as the sum of elements from A with the sum of with the elements of B. So in the same way, you can define the difference set, where the difference set of A minus B is nothing but small a minus small b, where small a is in A and small b is in B. And similarly, we can define the iterated set, K of A, which is the sum of the coordinates of the K tuples of A, and don't get confused it with uh, the set A scaled with the scalar K. It is different. It is basically the sum set of A with A K times. Okay. If you are new to this topic, just take a screenshot of it, because we are going to use these kind of definitions quite often after this. So this is called sum set. This is called difference set. And this is called iterated set. Now, what is additive structure? We say that it is a vague definition. First of all, it is not a actual definition. We say that an additive set A possesses strong additive structure if many of the solutions or many of the non-trivial relations A plus B equal to C plus D occurs. Why I'm saying non-trivial, because trivial cases such as A plus A equal to A plus A, we're definitely not going to consider that, right? So if there is a set where many of these kind of non-trivial relations A plus B equal to C plus D occur, we say that the set A possesses a strong additive structure. For example, take any AP, right? So in AP, suppose I have this AP, A comma A plus D, all the way up to A plus N minus 1D. Sorry, where N is a large integer. Then you can say that we can find so many of such relations, right? So that's why AP is a strong, AP possesses strong additive structure. Similarly, subgroups possesses a strong additive structure. And number of some such solutions is called the additive energy. I have also tell you that in the beginning of the lecture. It's called additive energy, and definitely large additive energy indicates strong additive structure. There is a special kind of set where we define the set as all the sums are distinct. That is, there are no such relations A plus B equal to C plus D for A comma B not equal to C comma D. This kind of sets are called Sidon sets. So there are many research going on regarding these Sidon sets. We are not going to talk about Sidon sets in today's talk, but it is very important in this subject. And Sidon set is once again has literally no additive structure, and it is very hard to study. That's why. So regarding this definition of additive structure, you can also define it like this. You can argue with the sum set definition. If this sum set A plus A, if the cardinality of this sum set is much less than the cardinality of A itself, then we say A possesses a strong additive structure. Because obviously then definitely you are going to get so many relations which will satisfy A plus B equal to C plus D, right? So we can argue it like that only. One can easily check that this cardinality of the sum set A plus A is upper bounded by A square, because there is cardinality of A many ways to choose the first element, and same for the second element. And it can be as low as the cardinality of A itself. So if the equality happens is this in this case, this is only possible if and only if A is a subgroup of the ambient group. This is a very kind of a trivial theorem. You can prove it by your own. And this kind of things happen when A is a seed-on set, as I've told you. So once again, why we study this subject is because of that, because this kind of additive relations or this kind of combinatorial structure reveals so many things about the set itself. So that is why the subject is so rich and so important. So there are some examples of strong additive structured set, like long arithmetic progressions, subgroup of the ambient group and all. Now, after knowing all of these definitions, it's time to move on to the proofs of the interesting theorems. And we are going to start with the most interesting theorem given by Ardosh. And the theorem is like this. Suppose you have a subset of, you have a set of integers, okay? You have a finite set of integers, suppose let it be A. Then what is the maximum such subset you can find inside A? That is sum free. Now, what is mean by sum free? Sum free means that no elements in B can be written as the sum of other two elements in B. Or in other words, inside B, we cannot find any A comma B comma C such that it will satisfy the relation A plus B equal to C. For example, if I take A as the set of integers 2, 3, 5, 80, then there is definitely a set where the relation 2 plus 3 equal to 5 gets satisfied. But if I remove this 5, then you can see that we get the subset B inside A, which is sum free. We cannot retain any elements in B as a sum of other two elements. So Ardosh asks this question in a general setting that if I get a set of integers, then what is the largest such subset we can find inside A? And the result is very beautiful. He has proven that it is also called as Ardosh sum free theorem. If A is any additive set of non-zero integers, then A contains a sum-free subset B, satisfying that the cardinality of B is always greater than the cardinality of A by 3. And why we're considering non-zero, if you ask, to avoid the trivial relations A plus 0 equal to A. Okay, in order to avoid these trivial relations, we are just considering non-zero integers. So if A is a set of non-zero integers, then A will always contain a sum-free subset B satisfying this inequality. And the idea of the proof is, or the proof sketch is, we are going to construct a B and we are going to argue on the expectation of that cardinality of B. And at the end, you will see that how beautifully this expectation of cardinality of B will exceed A by 3. Now, let's move on to the proof. So firstly, choose a prime of the form 3k plus 2 and choose the prime p equal to 3k plus 2 large enough so that we can fit A inside this particular set, minus p minus 3 to p plus minus p by 3 to p by 3. And definitely, since we are taking non-zero integers, we are excluding 0 here. Now, why to do this? Because we want to view A inside ZP, right? We don't want to we want to restrict ourselves in a finite ambient group instead of an infinite ambient group, which is a set of integers. So that is why I choose a prime P and large enough so that we can fit A inside this particular interval. And we are free to do so due to Dirichlet's theorem, because there are infinitely many primes of this form. Even if you don't know Dirichlet's theorem, you can just prove it by using Euclid's contradiction argument as well. So choose a P and construct this particular interval and put A inside that so that we can view A inside ZP. Now choose X from this set ZP uniformly and define this particular random set B, which is the elements of A, which can be written as X multiplied by any element from this integer set k plus 1 to 2k plus 1. There is another way to state that definition of B, which is all the elements in A such that X inverse A is inside this integer set. And this X inverse A is in ZP, by the way, it's not A divided by X. Now observe that this k plus 1 comma 2k plus 1, this sorry, this particular set is something in ZP. Now why is it something in ZP? Take two least elements k plus 1 and multiply, add them. What you are going to get is 2k plus 2k plus 2, right? So C is outside of this set. And even if you take the two largest elements, 2k plus 1 plus 2k plus 1, it is going to come out as 4k plus 2, which is congruent to k modulo p. We are working inside CP, remember? So it is congruent to k modulo p, which is just outside this set. Okay. So even if you add the two smallest element in inside a cyclic group and two largest element, you are going to get always you are going to get sum which is outside of that set. So definitely, if you do the same for any two elements inside of this set, it will remain outside of the particular set, right? So that is why this set is sum-free in ZP. It is quite trivial, honestly, and you can prove one beautiful uh, equivalence relation or if and only if criteria that if this set is sum-free in ZP, then it is also sum-free in Z. And the amazing thing is it is if and only if. Okay, so try to prove it. And since it is sum-free in ZP and it is sum-free in Z, we can say that it is also sum-free in B. And since it is sum-free in B, if I multiply any element with this integer set, that will also remain sum-free. So in particular, we have constructed B in a way such that B is sum-free inside A. Okay. Now we already have constructed B. Now we are going to argue on the cardinality of B. Now observe that the cardinality of B can be written as the sum of the indicator function, that A inside B, and summing it over all A. So what is indicator function? It is just a random variable which gives the value 0 or 1 depending whether A is in B or not. So if I sum it over all A, definitely we are going to get the cardinality of B, right? Now write this relation and take expectation in the both side. Okay. So expectation is linear, so we can definitely bring the expectation inside the sum. And expectation of indicator random variable is the probability itself. So expectation of B is sum of all the probabilities that A inside B. And we have just in the definition of the construction of B, remember I have written here. Let me go back. Sorry, here. This particular definition. That x inverse A is always inside this set of integers k plus 1 to 2k plus 1. So we are going to use that particular definition in this probability. That probability of A inside B is nothing but probability x inverse A is inside this set, right? And since we have chosen x uniformly, so definitely this x inverse A is uniformly distributed over all this ZP. So probability of A inside B for each A will be greater than 1 by 3. You can easily compute it by just using the formula of uniform distribution. The numerator will be 2k plus 1 minus k minus 1 plus 1. And the denominator will be the entire set, the cardinality of the entire set, this. And this will come out as 1 by, no, it will come out as k plus 1 divided by 3k plus 2. So definitely it is greater than 1 by 3. And no, sorry, 3k plus 1. We're not considering all the elements, we are excluding 0. So definitely it is 1 by 3 and greater than 1 by 3. And if I sum it over all A, we are going to get, oh, sorry. Yeah. If I sum it over all A, we are going to get the expectation of B is greater than E by 3. Now, expectation is nothing but in broad sense, it's just a weighted average, right? So definitely, if it is greater than cardinality of a by 3, then there is exists some realization which will satisfy, or there exists some choice of x such that this cardinality of b will satisfy it is greater than or equal to a by 3. So by this method, Ardash has proven that the existence of such sum free set B inside any set of non-zero integers A. And particularly this kind of uh, techniques like using expectation to derive something, these are very famous in the literature probabilistic methods in combinatorics. There is a very beautiful problem as well regarding this. It is not in additive combinatorics, but I have added that because it is very beautiful. Oh, okay. So before going into that, there is a generalization of the previous theorem that if A is a finite set of non-zero integers, once again the same setting, then there exists a subset B inside A such that the cardinality of B is greater than cardinality of A by n, and this particular equation has no solution in B. So in the previous case, we have done the same thing but with n equal to 3. Okay, so you can generalize it up to n, and the result will follow like this. So the idea is same. You just have to change the construction of B. You just have to choose the integer set wisely so that it will be sum free. Okay, inside ZP for whatever P you want to choose. So it is the generalized proof of that previous theorem. And now going into the interesting problem which I was talking about. It is that any 10 points in a 2D plane can be covered by finitely many disjoint unit disk. Now, why this problem is interesting, the problem also relies on the idea of uh, playing with expectations. And I really want that you guys try this by your own. This is a very interesting problem. And in fact, some mathematics YouTuber like three blue one brown, they also covered this question in their one of their posts. And mathematicians are also like working on this problem, and they have proven this theorem up to 14 points. And they have also found a configuration with 44 points when this theorem fails. So this is a very good theorem, and very researches are going on in this topic. So try this by your own. I have not covered the proof since it is not a part of additive combinatorics, but once again, it is a very good problem. So moving on to the next topic, some other useful probabilistic proofs. Now, in the previous proof, we did not use any higher probability, right? We just argue with the expectation. But for the next part of my talk, I'm going to derive some beautiful number theoretic results. And for that, we need some more powerful probabilistic tools. So here are the list of those probabilistic tools, or better to say probabilistic methods. So one is Markov's inequality. I think you guys already know about this kind of things. Markov's inequality, it gives the upper tail estimate of how likely x is to be larger than e of x. And then there is Borel-Cantil lemma, that suppose we have a sequence of events such that the sum of the probability of these events is finite. Then with probability 1, at most finitely of the events, EIs can occur. So if you don't know about these theorems, just take a screenshot, but don't bother about the proof because you can find the proof anywhere in any probability book. These are very trivial. We also have some improved way to estimate this x. So one is Chebyshev's inequality. It is you may say upgraded version of Markov's inequality. We use Markov's inequality to prove Chebyshev's, by the way. So if x is a random variable, then for any positive x, we can give a lower and upper tail estimate of this x with respect to the expectation of of the random variable. And why this is stronger than Markov, because here the decay is 1 by some quadratic, where in Markov you have seen that the decay is 1 by some linear. So these are very trivial inequality. The first non-trivial inequality is Chernov's inequality. Now, the inequality I have written here is not the standard Chernov's inequality. If you search it on Google or anywhere else, they will show something else, something including infimum or something like that. But for our discussion, we just need particularly this inequality, and it can be derived easily from the actual Chernov's inequality. So assume that we have a finite sets of random variables which are jointly independent. Okay, and there is an extra condition that the difference between that random variables with their expectation is at most one. Then define a new random variable which is the sum of all of these random variables. Then we can give the estimate probability of x minus ex greater than or equal to lambda of lambda into standard deviation, the same LHS that we used in Chernov's inequality, sorry, Chebyshev's inequality. But the RHS is much stronger. It is uh, at max 2 into maximum of e to the power minus lambda square by 4, e to the power minus lambda sigma by 2. So it is much stronger than Chebyshev's inequality, just for the one condition. Sorry, two conditions. One is jointly independent, and second is this xi minus e of xi is less than or equal to 1. So this is a very important inequality. I think I suggest take a screenshot of it. We are going to use it later. And why this is important? Because if you change these random variables, these jointly independent random variables, you are going to get different results, right? For example, if I take these random variables as Bernoulli random variables with probability p, okay, or Boolean random variables, then we are going to get another very beautiful corollary, which is this: let x equal to sum of n jointly independent Boolean random variables. Then for any positive epsilon, the probability x minus e of x greater than or equal to epsilon e of x is less than or equal to this particular term. And we can easily derive it from this. Sorry, from this. Just put lambda equal to, sorry, handwriting is better. Just put lambda equal to epsilon e of x divided by sigma. Put lambda, choose lambda like this, and you are going to arrive at this. Okay. You are also going to use one inequality, which is variance of x is less than or equal to e of x. So try it by your own. It is very easy to prove. I did not include the proof because it is a topic of probability, not additive combinatorics. And if you put epsilon equal to half in the above corollary, and like break this mod and bring x e of x here, we can say that x is equal to, or x is upper and lower bounded by some constant multiple of its expectation. This probability is greater than or equal to 1 minus 2 into e to the power minus e of x divided by 16. This is that Euler's constant. Now, above all of these inequalities, in the next proof, we are going to use this particular corollary. We are not going to use these things. Okay, don't worry about these max e to the power lambda by 4 and all. We are just going to use this, but in order to show you that how we are getting this particular inequality, I needed to show you the actual Chernov's inequality and its corollary. Wait a minute, I'll be back in 1 minute. Okay. Okay, so I'm back and let's go into the topic. Yes, so we are going to use this boxed inequality. So remember this or write it down somewhere else, because this is a very strong result, by the way. So now we are going to show you that how this additive combinatorics or probabilistic methods are used to derive some number theoretic results. Now, in order to dive into number theory, first, once again, we need some definitions, and these are very easy definitions. So let's define basis. So what is the basis? We suppose take a set of natural numbers, okay, and most of the time it is infinite, okay. It may be finite, but most of the time it is infinite. So take a subset of the natural numbers and take any fixed positive integer. Then we define the counting function r k comma b of n for any n in natural number as the number of ways we can represent n as a sum of k elements of b. So as you can see in the definition, right? Uh, it is a definition of the counting function r k comma b, and it is very important because it is used to bound the density of any sequence of natural numbers. So I'm going to show it how, but for now, this is the definition of counting function. And we say that B is a basis of order k if every sufficiently large positive integer can be represented as sum of k elements of B. Or in additive combinatorics notation, B is a basis of order k if and only if the set of natural numbers minus this sum set b plus b up to k times, or also written like this, n set minus kb, it is finite. That is, after a certain n, we can represent any natural number as a sum of k elements of b. Okay. So in order to clear your concept, let me give some examples, and it will also show you how it is related to number theory. So there are some examples of bases. The most famous four examples. First is Lagrange's theorem. So he said that in any number can be represented as sum of four squares of, right? So the square of natural numbers 0, 1, 4, 69, 16, these are known to be basis of order 4. Similarly, regarding Goldbach conjecture, the primes are conjectured to be a basis of order 3. No one has proven that. Vinogradov's theorem, the set of all primes are basis of order 4. That every sufficiently large natural number can be represented as sum of 4 primes. And the most important in additive combinatorics, that is Warning's conjecture. And it is first proven by Hilbert, the one guy, Hilbert basis theorem. The conjecture says the kth power of natural numbers are known to be basis of some finite order. Okay. So it is the Warning's conjecture, and once again, many researches are going on in this direction. So these are some example of basis. And once again, Ardosh has proven one of the fundamental theorem regarding this basis. Not exactly basis, but better to say thin basis. Now, what is thin basis? So, going to get into thin basis later, but first, let me show you that why counting function is important. Remember, I have told you counting function is really important in order to estimate the density of some sequence of natural numbers. So what is density? Density is this term. Suppose we have a sequence of natural numbers and write that set as B. Then density is, this is called density of that sequence. Okay. So as you can see that given a counting function r k comma b, we can bound the numerator of any such density function as this. And why so? In the counting function's definition, r k comma b of n is nothing but the number of ways we can represent n as sum of k elements of b. So basically, number of ways or number of solutions of this particular equation. Right? Sorry. Now, if I take, as you can see, n less than or equal to n, then definitely no xi can be more than the capital N, because since all the xi's are non-negative, definitely that will be more than that will get outside of this set. Okay. So if n is less than or equal to n, definitely all these xi's has to be less than or equal to capital N. That is why the set of all the solutions of such equations for n less than or equal to n will lie inside the set B intersection 0 comma n k times. So that is why it is a subset of this, and that is why this relation is there, because the cardinality of the all the solutions of these sets are just nothing but just summation. And similarly, you can show the upper bound like this, where the summation is taken up to k multiplied by capital N for any n greater than or equal to 1. Now, if I divide it with the cardinality of n, we are going to get the estimate of the density function. And in number theoretic style, anyone wants to say anything? Okay. Okay. Or in number theoretic style, we can say that the cardinality of this set B intersection 0 comma n, it is omega of n to the power 1 by k. Okay, you can derive it from here, this particular thing. Now, what is thin basis? Okay, so a basis of B of order k is called thin basis if this counting function is upper bounded by some constant multiple of, or the growth of this counting function is upper bounded by some constant multiple of log n for large n. Then we call the basis B as a thin basis. And it also implies, if you put this particular definitions condition rk comma b of n equal to big of log n inside this boxed inequality, you can improve this density bound like this: cardinality of B intersection 0 comma n, or the number of natural numbers less than n which is inside B, it is n to the power 1 by k plus small o of k. Small o subscript k means the decaying constant will depend on k. Okay, so that's it. That is the definition of thin basis. Okay, now Ardosh proven that for any k, for literally any k, we can find a thin basis, and this is a very strong theorem. But the general proof for any k, that is a bit difficult, and it requires a lot of time. So I've just proven the case for k equal to 2, and you can just do it for k in natural number. Okay, so it is also known as Sidon's problems on thin basis. It is also proven by Ardosh. There exists a basis B of order 2, so that this R 2 comma B n is theta of log n for sufficiently large n. In particular, there exists a thin basis of order 2. And regarding basis, there is a very big conjecture, also known as Ardosh-Student's conjecture, that if B is a basis of order 2, then always this limits of R2 comma B of n will tend to infinity. So this is out of our reach, because it is a very old conjecture, and till now no one has proven this. But we can definitely prove this particular theorem. And in order to prove this theorem, we need the corollary of the Chernov's inequality. So remember, in that inequality, we in the LHS we got something like this. So I think you can guess that how we are going to get that theta notation in the proof. So let's dive into the proof. And the idea is same. In most of the probabilistic techniques, the idea is same. Just construct a P in a, under some probabilistic restriction, and then argue with the cardinality of that B, or whatever you are needed. So once again, we are going to do the same. Define a random set B by recurring the events n in B with jointly independent probability that P, that probability n is inside B with this probability minimum of C square root under log n by n comma 1. And we have keep C arbitrary, because we will put the value of C as per our convenience. So we have written that C is a large constant which will be chosen later. For now, we have constructed B where the probability that each natural number is inside B is this. Now, the counting function R2 comma B, we can define it like this: summation of identity function I inside B into I j inside b where I plus j is equal to n. Now in counting function, remember the definition was how many ways we can represent n as sum of two elements of b, for this case particularly because k equal to 2. So we can definitely write it like this, because this term will be 1 if I inside b, this term will be 1 if j is inside b, and since the sum is taken as I plus j equal to n, definitely that will take respect the definition of counting function. And since both is inside b, this will give the output. If any of this is outside b, then definitely 1 is 0 and we are going to get 0. So we are not going to get any output. So this is a very smart way to write the counting function. And it is also equal to theta of this particular term, where you have restricted I from 1 to n by 2, indicated I inside b, indicated n minus I inside b. Now why this is theta of this? Write this sum as Sn. Okay. Now see that in Sn, we are considering I comma j, where I plus j equal to n. That's it. We're not considering j plus I. We are considering both I plus j and j plus I individually in this case. In the definition of Sn, we are going to consider this once. And that is why if n is even, then, if n is odd, then 2 of Sn is equal to this term, or b of n. And if n is even, and there is an n by 2 inside b, then definitely we are going to consider this term as well, right? Multiplied. So for that particular case, I have written this big of 1. So if you are not clear, or if you are like have a doubt, just do it by once. Do it by your own once again, because it is quite trivial. Okay. So now, given this particular ugly term, our aim is to show that the probability that this term, that this ugly term is equal to theta of some log n is positive. Now, since theta is transitive, if I can show that this is positive, we can definitely arrive at our what can I say? Arrive at our desired result. So our aim is to show that this is positive for all but finitely many of n for some suitable choice of constant in the definition of n. Now, how we are going to do so? So once again, I have constructed B. Now we have to argue on its other combinatorial properties. Take expectation of this particular set. Linearity of expectation will go inside. And if you compute this, since I have taken the probability n inside B as c into log n of n, remember, we can write the probabilities directly here. Log I by I and square root under log n minus I by I and c square plus OC of 1. Once again, OC of 1 means a constant that will depend on C, the choice of C. That's why subscript C. Now this is equal to this ugly term, and now there is a reasoning behind that. Now why this is equal to that? We can write log n minus I divided by n minus I as log n plus some big of 1 divided by n into 1 minus I by n. Okay, so definitely this is equal to some theta of root under log n by n, because it is, and okay, so this term can be replaced as with this. Now why I have taken theta outside? Because this theta is uniform over the definition of square root under log I by I. Uniform means there exists a particular upper bound and lower bound in terms of square root under log n by n, such that we can put every square root under log I by I inside that bound. So that's why we can say this theta is uniform, and we can bring this theta outside this summation and like basically interchange the theta and the summation, and we can write it like this. Okay, so this square root under log n by n is that term, and let me clear the board. And OC of 1 is as it is. And if you compute this, this is a number theoretic, not number theoretic, but it is a very good exercise. If you compute this, this will come out as root under in log n. So basically, if you multiply this with that, we are going to end up with theta of c square log n plus some constant. In particular, by choosing c large enough or choosing c suitably, we can bound our desired term as any way we want. So for our case, we have bounded this expectation from 32 log n to some kappa log n, where kappa is greater than 32. And the restriction I less than equal to n by 2 makes the random variables Boolean, because once again, we are not going to take the repeat cases so that they will be like dependent. So this particular restriction I less than n by 2 makes the Boolean random variables jointly independent. And if I now apply the previous mentioned corollary, remembered that probability of x equal to theta of e of x is greater than 1 minus e to the power something. If I apply this here, that corollary of Chernoff's inequality, and apply the Bodel-Cantel lemma, you don't even have to use Bodel-Cantel lemma. If you apply this inequality, and if you argue that since this expectation is some theta of log n, and we are going to consider n too large, then definitely that term will go to 0, and you are going to get probability that this term is theta of log n 1 almost surely. So basically, from that we can say that there always exists a basis B such that there always exists a basis B such that this R2 comma B of n equal to theta of log n, because this particular term I in B, I in minus I in B, it is nothing but R2 comma B. So this is a very good result by proven by Ardosh once again. And regarding this, we can improve this, or better to say, we can generalize this by choosing k any natural number. For any fixed k, there exists a subset B inside n such that Rk comma B of n equal to theta of log n for all sufficiently large n. Or in particular, there exists a thin basis of order k for any k. Okay. So it has quite a bit significance in number theory, as you can see. Now there is another definition named complementary basis. It is as simple as basis as well. So given a set A and a fixed integer, positive integer, and a set B, we say B is a complementary basis of order k of A, if and only if every sufficiently large natural number can be written as a sum of an element in A and k elements in B. Okay. Or equivalently, if once again, if n minus A plus kb is finite. So here we are doing the same thing, but instead of just remove one B and add one A instead. And you get the definition of complementary basis. There is a definition of complementary basis, and regarding this, we can also define the what can I say, counting function analogously as the previous case. R subscript A plus B up to k times n. It is equal to number of ways we can write n as a sum of a element of A plus k elements of B. Okay. And similarly, we can like argue on the density function of this particular term like this. And these ideas are similar. That's why I am not going to invest any much time here. And now this is the most important theorem of Paul Ardosh in this literature, including complementary basis. Suppose P, which is a set of all prime. The theorem is the set of all primes has a complementary basis B of order 1, such that this B grows. The growth of B is upper bounded by log square n for all sufficiently large n. And why there this term log square n appears, that is related to many number theoretic problems as well. I really want that you do some research on this, because proof is quite long, and you can refer to the Terence Tau's book on additive combinatorics if you want to see the proof, but the proof is quite long and it needs some more probabilistic results. But it is a very beautiful thing, and it is very relations with modern number theoretic results as well. So that is for number theory. Now, for the last part of my talk, I'm going to show that how it is applied in other branches of mathematics, mainly in combinatorics. So, in order to prove the combinatorial results using probabilistic methods, we need some more probabilistic tools. So, one of the tool is Lova's local lemma. So, it is once again, it is another very known theorem in probability theory. So suppose we have a finite family of events. Okay, so V is a finite set, or V is a like indexing set which is finite. And for each I in V, there exists a set gamma I such that AI is mutually independent of all the edges where J is not inside this gamma I. And assume further that there exist some real numbers such that we can bound the probability of each event in terms of these real numbers, like this. Then for every I, we can say the probability that all the complement of the event occurs. So this is a fancy way of writing the intersection sign. It emphasizes and. So the probability that all the complements of the event occurs is at least the product of all 1 minus xi's where I is in V, and in other words, it is greater than or equal to, greater than 0. Okay. So once again, we don't need Lova's local lemma. Instead, we need the corollary of this, which is also known as symmetric Lova's local lemma, or SLLL in probability theory. So it says that suppose we have a finite family of events, and where the probability of each event is less than or equal to P, and each AI is mutually independent of all but at most D of the events, and we have this particular inequality, EP plus 1 is less than or equal to 1, or you can write it like this. You can bound P basically like this, 1 by E D plus 1, where this E is once again Euler's constant, that 2.71 something. Then this probability of this event, that the complement of all event occurs simultaneously, is at least this particular term, or the main result is it is greater than 0. Okay, so this is the main result. So using this particular theorem, we are going to prove one of the problems in colorings, not graph colorings, but which is known as real number coloring. It is more likely some analytic results rather than some graph theoretic results. But once again, graph theoretic results are related to this. So let's see. So what is the coloring of a real line? So coloring is basically a map from set of real numbers to 1 comma k, where each integers in the set 1 comma k depicts one particular color. And we say that a subset T of R is called colorful if it contains all k colors. Or in other words, coloring is a map from R to this 1 comma k, and if we restrict this map to T, and if this restriction is surjective, we say that T is colorful. Okay, it is the analytic way to say this. So once again, Ardosh has proven another good result. Let M and K be two positive integers satisfying this extremely ugly inequality, but it is not that ugly that you as you think. We are going to like dilute it down. Let M and be two positive integers satisfying this particular inequality. Write it down in your notebook or take a screenshot. Then for any set of real numbers with cardinality M and any subset of real numbers, there exists a k coloring of R such that the translates x plus s of s are colorful for every x in s. Now this is a very non-intuitive result. Okay. And what do you mean by translate? So suppose take a real set of real numbers with cardinality M. For example, I take M equal to 3 and I take s equal to 1 to 3. And I take the subset x in R, as square root of all primes. Okay, it is a set root under 2, root under 3, and all. So the translates of S means the set 1 plus root under p, where p is inside the prime set. Okay, 1 plus root under p, 2 plus root under p, and these kind of things. So the theorem says that if I can define a map from R to 1 comma k, then definitely these restrictions are going to be surjective. This is very strong. Okay, this result is quite strong, but the proof is as simple as it can get. So take the screenshot of this theorem, and we're going to prove the theorem now. So we are going to prove it for the finite case when x is a finite set, and I think you know quite a bit of matrix space topology using compactness, Tikhonov's theorem, and all. You can like extend this result to infinite case as well. I leave that. Our main interest is to prove this theorem. So we first prove the theorem when x is finite. I left that infinite case for you guys. Now, assume x is finite. Since S is also finite and x is finite, the sum set x plus s, it is also going to be finite. And once again, we are only interested in the coloring of the points inside the subset x plus s, because every translate small x plus s is inside x plus s, right? So we are going to work inside this sum set. Now color each of the point of this sum set independently with probability 1 by k. We have k colors. Now color each of the points in the real line with uniform probability 1 by k. So for each point in x, let x denote the event that the translate x plus s is not colorful. So our goal is to show that the probability that the complement of all these event is greater than 0, or in other words, there exists a case where these translates are colorful with probability 1. So if this happens, then every translates x plus s is colorful. So that is the like probabilistic breakdown of our problem. Now once again, estimate fix x in S. Now since the cardinality of S is M, the translates x plus s contains exactly m many points. Okay, and we call ax is a bad event if at least one color is missing from the translate x plus s. So without loss of generality, assume that the color 1 is missing. So for a particular given point of x plus s, the probability that the point is not colored 1 is definitely the total probability, that is 1, minus the probability that the point is colored with 1, that is 1 by k. And breaking it down will give you 1 minus 1 by k. And since the coloring is independent, we can extend this to all the points of x plus s, that the probability that color 1 is missing from x plus s is this particular term multiplied by itself m times, because the cardinality of x plus s is m. So it is like this. And we can extend this again to all the sum set x plus s by the union bound of probability. So the same estimate holds for every color, right? So since there are k colors, the union bound gives probability a of x is less than or equal to k into 1 minus 1 by k whole to the power n. So we know the union from the union bound, it is less than or equal to I1 to k multiplied by the probabilities, probabilities of individual events, which is this. So it is equal to that. Now define this RHS as P. Then we can say that P A of x is less than or equal to P for all x in x. So observe that we are slowly getting to our desired construction, because we want to use the symmetric Lovász local lemma, right? So for that we need a bound of the probability of the events, an upper bound. So we got that. Now for the rest of the ingredients. Okay. Now the event Ax, okay, depends on the coloring of the points inside x plus s, obviously. Therefore, if x plus s intersection x dash plus x, where x and x dash are from a capital X, is equal to null, then only ax and ax dash depend on disjoint set of random variables, because if there is some element inside this intersection, definitely then trivially one element will be dependent, right? So ax and ax dash cannot be disjoint set of random variables in whole. So there will be so this disjointness criteria is necessary. Hence, ax and ax dash are independent. So we need this particular disjointness criteria. Now, when this dependence occur, when definitely this particular intersection is not null, or in other words, there exists s1 and s2 in S, such that x plus s1 equal to x dash plus s2. Rearranging, we can get x dash equal to x plus s1 minus s2. So every dependent translate arises from a difference s1 minus s2. So each of the unique differences will give a rise to each of the unique dependent criteria. So remember, in symmetric lowest local lemma, we have mentioned one particular line that xi's are mutually independent, except at most d many events. So we are going to construct that d now. So that's why we are like chanting these dependents again and again. So every dependent translate arises from the difference s1 minus s2. And definitely there are m into m minus 1 many ordered pairs s1 comma s2 with s1 not equal to s2. So for a fixed x, there are at most m into m minus 1 many possible values of x dash such that they are dependent. So each event x is independent of all but at most the many other events. Now we have put all the ingredients to like create the symmetric lowest local lemma. Now you are going to put it in order. Okay. So let's apply the lowest local lemma. We have shown that each probability, the probability of each event is upper bounded by this p, which is k into 1 minus 1 by k to the m. And each x depends on at most d many other events. So the hypothesis of the theorem was this particular thing is less than or equal to 1. And now if you put the values of d and p, you are going to get that exactly that ugly term that we saw in the beginning of the proof. So under this particular assumption, or under this particular choices of k and m, the symmetric lowest local lemma implies that the probability that all the complement of the events occurred is positive. Means there exists a coloring for which no bad event occurs, or in other words, there exists a choice such that every x plus s is colorful. So this once again, this proves the theorem when x is finite, and the general case follows by a standard compactness argument. So once again, I this is a bit boring proof because the proof is quite long, but if you do it by your own, or if you write it down somewhere else, you can understand the beauty of the proof. It is amazing. Now, it is the coloring of a real line. You can also prove some beautiful graph theoretic results as well using this probabilistic methods. And one of the most beautiful result is this. It is also used in extremal graph theory. Okay, I'm not going to prove this, and this is the last slide. So once again, guess who has proven that? Artosh. And he has proven that there exists a positive constant c greater than 0, such that for all sufficiently large integers, there exists a graph on n vertices which contains no triangles and no independent set. So independent set is basically a set of vertices where there is no edge between any two vertices inside that set. That's called an independent set. So once again, you can see that this is a very strong result in extremal graph theory. And once again, probabilistic methods are used to prove this particular theorem. And try this by your own. The idea is not as similar as the previous proof, but the proof is very beautiful. So this is all for today's talk. I think I have motivated you guys enough to study this subject and show you the significance of this subject in different mathematical branches. And if you want to study this subject in depth, I will suggest the book Additive Combinatorics by Terence Tao and Wu. I'm also studied that book. So thank you. Is there any questions or?
So, are there any questions for the speaker? If not, then we can thank our speaker. Thank you, Devatrila, for the talk. Okay, we have a question.
Yes,
Can you share?
yeah, the book's name is Additive Combinatorics by Terence Tao and Van H. Fu. You can find it on the in the internet as well, PDF format.
Okay, then we
Is
can
there
end the
any other
meeting here.
questions?
Okay, if there are any other questions.
Hmm.
Thank you, Devatrila, for the talk.
Thank you.